There's a very special number. It has the property that when it is multiplied by itself, it gives -1. This number was discovered by a Greek mathematician and philosopher something like 2,500 years ago. But it was thought to be completely useless, and that's why it was called imaginary. This imaginary number, which is sometimes denoted by the Greek symbol iota, or we simply call it I, turns out to be of exceptional importance. And when it is combined with a real number, then it leads to a complex number. Complex numbers today are central to mathematics, but not just to mathematics, to physics, and even to electrical engineering. So when you have complex circuits, you have to use complex numbers. We're going to begin our study. It'll just be scratching the surface, but let's get on with it.
Let's begin by considering one of the simplest possible quadratic equations, x squared plus 1 equals 0. Or, if you like, x squared is -1. The question is, how do you solve this? Now, there is no number that we know of up till now which is able to solve this equation. But if we agree to have a new kind of number, and rightly or wrongly we'll call this an imaginary number, and this has the Greek letter iota associated with it, I squared, if defined as -1, will allow us to solve this equation. The solution will be x is either plus iota or x equals minus iota. So this iota, or I simply, being the square root of -1, so if you write I squared is equal to -1, you could equally write this as I equals square root of -1, and it would carry the same meaning. Now, this x equals plus square root of -1 or x equals minus the square root of -1, both solve this equation. And of course, they solve equations like this as well. So if we ask, what is x squared plus 9 equal to 0? What's the solution of this? The answer is x is either plus 3i or x equals minus 3i. This, therefore, is a very useful number, and without it, we wouldn't be able to solve equations like this or like this. But now, let's look at an equation like this. X squared plus x plus 1. Now, that's a little bit more complicated, but it's actually very similar to this, because we could write this as x plus a half squared plus 3 over 4 is equal to 0. Just open this out, and this is exactly the same as this, which means that we can write this as x plus a half squared equals minus 3 over 4. And then this, of course, is the same as x plus a half equals either the positive or the negative square root of minus 3 over 4. And so from here we get two possible solutions. X is minus a half minus square root of 3 over 2i, or x is minus a half plus square root of 3 over 2i. And so using this symbol I or iota, we're able to solve this. More generally, if we had something like this, ax squared plus bx plus c equals 0, then we'd solve this in the usual way. X equals minus b plus or minus square root of b squared minus 4ac over 2a. And again, if what was inside over here was negative, then we would get an imaginary number once again. So you see that for quadratic equations, it is absolutely essential to have this square root of -1 defined. And this is true even for cubic equations. So let's say that you had ax cubed plus bx squared plus cx plus d equals 0. Now, this sort of equation would also need the square root of -1 to solve it. Using the symbol iota or the imaginary number I, we'll make complex numbers. So, for example, 3 plus I into 2 is a complex number whose real part is 3 and whose imaginary part is 2. Imaginary because it multiplies iota, the square root of -1. In general, a complex number is frequently denoted by the symbol z, and it has a real part a and an imaginary part b. Now what we'll learn are the rules of adding, multiplying, and dividing complex numbers. But first, let's say that two complex numbers z1 and z2 are equal. What does that mean? It means that z1 is a1 plus I b1, and z2, which we'll call rather a2 plus I b2, these two will be the same only if a1 is equal to a2 and b1 is equal to b2. So we say that two complex numbers are equal if their real parts are equal and if their imaginary parts are equal. Let's now get to the rules for addition of two complex numbers. So if I have z1 as a1 plus I b1, and if I have z2 is a2 plus I b2, then we add them together in a perfectly normal way. So z1 plus z2 means that you simply add up their real parts and you add up their imaginary parts. So b1 plus b2. It couldn't be simpler and more obvious. That, of course, is what you want. a1 plus a2, b1 plus b2, they make this new number z1 plus z2, and if you like, you can call this the new complex number z, which is got by adding these two complex numbers. Now let's talk about the multiplication of two complex numbers. Again, z1 will be a1 plus ib1, z2 will be a2 plus ib2, and let's ask what is the meaning of z1 times z2. Well, that means a1 plus ib1 multiplied by a2 plus ib2. And we'll do this again in a very natural way. a1 times a2, then I times a1 b2, and then I times b1 a2, and finally I b1 into I b2, which is I squared b1 b2. And so since I squared is -1, we can write this as a1 a2 minus b1 b2, and then we'll take iota or I common and write this as a1 b2 plus b1 a2. So the result of multiplying these two complex numbers, z1 and z2, is another complex number whose real part is this and whose imaginary part is this. Now this was perfectly straightforward. The only thing is that we kept the i's separate and we realized that this I squared over here is -1. That's what gave the minus sign over here. Let's now come to the division of two complex numbers. So I want to divide z1 by z2. So let's write z as z1 divided by Z2, and that's A1 plus IB1 divided by A2 plus IB2. Well, what are we going to do over here? What we want is something that's of the form real number plus I times another real number. So let me write the same thing as is over here and then multiply by A2 minus IB2 and divide by A2 minus IB2. So I multiply and divide by the same complex number. The advantage of doing that is that at the bottom, I'm going to get A2 squared minus I A2 B2 and then plus I B2 A2. Those are going to cancel. And then when I have I times B2 into minus I times B2, this whole thing will give me A2 squared plus B2 squared. So now let's work out the numerator over here. That is A1, A2 minus I A1 B2 plus I B1 A2 and then I into minus I, so plus B1 B2, and it's all to be divided out over here by A2 squared plus B2 squared. So now we can separate this out into the real and the imaginary parts, and what we'll get is A1 A2 plus B1 B2 divided by A2 squared plus B2 squared, and that's the real part. And then there'll be an imaginary part which will be plus I into B1 A2 minus B2 A1 divided by the same. So the common denominator, which is A2 squared plus B2 squared. That's how you divide two complex numbers. You get a real part and an imaginary part after making the denominator real. Having defined a complex number, we'll now define the complex conjugate of that number. The word conjugate means partner. So, suppose that x plus iy, we'll call it z, is a complex number, then z star is called the complex conjugate of z. What that means is that the imaginary part gets a minus sign instead of a plus sign as over here. There are a number of very obvious properties that follow. So, if I take a complex number x plus iy, then of course z star is x minus iy. And if I take the complex conjugate of z star, so the conjugate of z, well, then I have to change the sign of I again, and so that becomes x plus iy, and that's z. So z star star is z itself. Let's take another one. If z is equal to z star, then that means that z is real. That is to say, it has no imaginary part y to it. Next, if I add two complex numbers together like this, and I take their complex conjugate. So I take the complex conjugate of the sum of two complex numbers. That's equal to z1 star plus z2 star. And that's actually quite trivial to see, because if I take z1 plus z2, and z1 is a1 plus ib1, and z2 is a2 plus ib2, then this is a1 plus a2 plus I times b1 plus b2. And let's say that I take the star of this, then the only thing that I have to do is change the sign over here, and so this over here instead of a plus will become minus, and that's exactly what I get by adding Z1 complex conjugate and Z2 complex conjugate together. So that's very trivial to show. It's equally trivial to show that if I have 1 over Z and I take the complex conjugate of that, then that gives me 1 over Z star. How do I do that? Easy, because I will write 1 over Z first of all as this thing, 1 over A plus IB. And now if I take the complex conjugate of this, that's equal to the complex conjugate of this. But now write this as A minus IB, and I divide by A minus IB as well, of this thing, A plus IB, and I take the complex conjugate of that. So I've just taken 1 over A plus IB multiply by 1, that is multiplication division by the same amount, and now that's equal to A minus IB divided by A squared plus B squared. And then when I take the complex conjugate of this, I get A plus IB. On the other hand, if I started out with 1 over Z star, well, that would be 1 over A minus IB, and then I'm going to multiply this by A plus IB, divide by A plus IB, and this then gives me A plus IB, and then when I multiply out the denominator, I get A squared plus B squared, and so this and this are exactly the same. Similarly, and there's not space enough to make another point, but that's equally trivial to show, that if I have Z1, Z2 star, complex conjugate in other words, that's the same as Z1 complex conjugate multiplied by Z complex conjugate. So if you take the product and then take the complex conjugate, or you take the product first of the complex conjugates, the two are identical. We'll now solve a number of simple problems using the principles that we've just learned. First, we're asked to solve for x and y the equation 1 minus I squared plus 2 into x plus iy equals x minus 2iy. 1 minus I squared is 1 minus 2i plus I squared, but that's minus 1, plus 2x plus 2iy, and that has to equal x minus 2iy. The real part on the left-hand side is 1 minus 1, which is 0, and then there's 2x. The real part on the right-hand side is just x. So this equation has solution x equal to 0. Now, look at the imaginary part. That's minus 2 on the left-hand side, and then there's 2y. And on the right-hand side, it's minus 2y. And so that gives us 4y equals 2, which means y is equal to a half. So y equal to half, x equals 0 is the solution to this equation over here. We'll use the same principles for solving this equation over here for z. But first, let's take 1 plus I over 1 minus I and simplify this a bit. So to do that, let me multiply by 1 plus I over 1 plus I. That's to make the denominator real. At the top, I will get 1 plus 2i plus I squared, which is minus 1. At the bottom, it'll be 1 minus I squared, which is 1 plus 1. And so at the top, we have 2i. At the bottom, we have 2. And so this over here is just I. When you square it, you'll get minus 1 plus 1 over z equals 1 plus I. And certainly that's easily solved. 1 over z then is equal to 2 plus I. And so z is 1 over 2 plus I. And now let's get that into the standard form by writing this as 2 minus I and dividing by 2 minus I as well. So that's 2 minus I divided by 4 squared plus 1 squared, which is 5. And so finally we get the real part to be 2/5 and the imaginary part to be 1/5. That is the solution for z. There's an important difference between complex numbers and real numbers or ordinary numbers. For a real number, you can always say that this real number is bigger than that real number. So, for example, 3.79 is bigger than 2.88. But you cannot say that this complex number is bigger than that complex number. That makes no sense. However, you can define what is called the magnitude or the size of a complex number. And you define it in the following way. Suppose z is the complex number a plus ib. Then you define the magnitude of s as the positive square root of a squared plus b squared. Not the negative sign, the positive sign. And obviously, if I have z star, that's a minus ib. Well, in that case, the magnitude of z star is exactly the same. It's also a squared plus b squared, and so the two are equal. Let's work out a number of properties now. First, obviously, if I take z star, that's a plus ib into a minus ib, and that's a squared plus b squared, and so that's obviously z squared. More generally, if I have z1, z2, and I take the magnitude of z1 into z2, I claim that that's magnitude of z1 into the magnitude of z2. And that's actually very easy to prove, because if I have z1, z2, and I multiply it by its complex conjugate, so z1, z2 star, well, that's the same as z1, z1 star. That's because when you take the complex conjugate of z1 into z2, that's z1 star, z2 star. And so that's what we have over here. And this is z1 squared, and this over here is z2 squared. And this, obviously, here is the magnitude of z1, z2 squared. So the magnitude of z1, z2 is the magnitude of z1 into the magnitude of z2, as is over here. An important property of the modulus is that if I have two complex numbers z1 and z2 and I add them, and then I take the modulus, then this number is always less than or equal to the sum of the moduli of z1 and z2. Now, to illustrate that, let me take z1 equal to, let's say, 1 plus I, and let me take z2 equal to 1 minus I, in which case z1 plus z2 is equal to 2, and obviously the magnitude or the modulus of z1 plus z2 is then 2. On the other hand, the magnitude of z1 is clearly square root of 2, and the magnitude of z2 is also the same. So let's compare 2 with 2 times square root of 2. Clearly, this condition over here is fulfilled. Unfortunately,
This property over here is not so easy to prove. It will take more time than we have in this lecture. However, I would encourage you to go and read the proof.
Let's now look at this problem, where we are asked to sketch all points z which satisfy the condition that the magnitude of z minus I is 1. The way we should read this is that this is the distance between the point z and the point I. The point I is, of course, over here. And the distance between z and I must always be 1. Now, if you look at this, immediately the thought comes that this is a circle whose radius is 1. And so it's something that will go around like this. And this is the point z. And this is the point I. This here will be the distance z minus I. And that is 1 for every point on this circle. So you see how extremely easy this is. If you read it in the way that it's the distance of z from the point I, which is fixed and has value 1. But now let's confirm this in another way. So this is saying, equivalently, that z minus I squared is 1. And then I'm going to write this as z minus I into z minus I complex conjugate is 1. Then this is z minus I into z complex conjugate plus I equals 1. When we expand this out, this is z star plus I into z minus z star plus 1 equals 1. Okay, so we cancel the ones over here. And now I'm going to write z equals x plus I y, which means that z star is then x squared plus y squared. And this z minus z star, so you see if z is this, then z star is x minus iy. Z minus z star will then be 2iy. And that is multiplied by I, so it's I squared, and that's equal to 0. Now, that's saying that x squared plus y squared minus 2y equals 0, which I can then write as x squared plus y minus 2y plus 1 equals 1. I've added 1 to both sides, and then this over here is x squared plus y minus 1 squared equals 1. And that, of course, you recognize as being the equation of a circle whose center is at y equal to 1. So we've checked that if you write this out in terms of x and y coordinates, that you do indeed get this circle. But certainly, it's a much harder way of going about things. Now that we know what the magnitude of a complex number is, we know that is just a number. So the magnitude of z would be 2 or 3 or 9.2 or whatever, and so we can add, subtract, multiply, divide with this number. And so if I write z in the following way, you will not mind it because I am just multiplying and dividing by the same number, and this over here is just 1. But I can write this slightly differently. Let me write this as magnitude of z into z over magnitude of z. So this over here is a complex number with magnitude 1, meaning that if I take z over z and take its magnitude, well, that's 1. And that's pretty obvious. Now, I'm going to write this complex number with magnitude 1 in a peculiar form. I'm going to write this as cosine theta plus I sine theta. Now, obviously, this has got magnitude 1 because if I take the square root of the real part squared, what we called a earlier, that's cosine squared theta, and the square of the imaginary part, sine squared theta, well, that's equal to 1. We all know that. And so, therefore, any complex number with magnitude 1 can be written as cos theta plus I sine theta. More generally, you could write any complex number as z equals r into cosine of theta plus I sine theta, where this r is the magnitude of z. And so you could say that x is r cosine theta, y is r sine theta, and r is therefore the square root of x squared plus y squared. But then this over here gives us a certain picture of how to represent a complex number. We'll discuss now how to represent complex numbers. This is called the complex plane. So let's write our complex number as x plus iy. X is the real part, y is the imaginary part, and let's say we want to look at the complex number z equals 2 plus 1 times I. Well, that would mean that we would go 2 units along the x-axis and 1 unit along the y-axis, and this would be the complex number 2, 1. That is to say, the imaginary part is 1, the real part is 2, and this is this number. If I wanted to look at, let's say, z equals 2 minus I, so actually I should just get that by complex conjugating the above, then that would mean going 2 units this way and 1 unit this way. So this here is 2 minus 1. And of course, the magnitude of this we would get by drawing this line over here. This is r. This r will be the square root of 2 squared, which is 4, plus 1 squared, and that's square root of 5. So this is the magnitude of this complex number over here. Now, we just discovered that we could write x as r cosine theta and y as r sine theta. So that makes it very obvious that this over here is the angle theta. So this from here to here is x, and from here to here is y. And of course, r is the square root of x squared plus y squared. This representation of z in the complex plane, also called the Argand diagram, is very useful when we want to multiply two numbers with each other. So let's say that you had z1, which was the magnitude of that complex number r1, times cosine of theta 1 plus I sine of theta 1. And you had a second number, z2, which was r2 cosine theta 2 plus I sine theta 2. And now let's multiply these together. Then z1, z2, which you can call a new complex number. This would be simply r1, r2, and then you multiply cosine theta 1 with cosine theta 2, which is cosine theta 1, cosine theta 2. Then this I sine theta 1 into I sine theta 2, you'll get I squared, which is a minus 1. So that's minus sine theta 1, sine theta 2. So that is the real part, and there'll be an imaginary part as well. So let's write the imaginary part over here. That's I times, now sine theta 1 cosine theta 2, and then there is also sine theta 2 cosine theta 1. So we have this term here as well. And now this term over here, cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2, this is simply r1 r2 cosine of theta 1 plus theta 2, and this term over here is I sine of theta 1 plus theta 2. That's simply by means of the trigonometric functions that we already know. And so this then is how we multiply two complex numbers which are of this form. We simply multiply the two magnitudes, r1 and r2, and we add the angles theta 1 and theta 2. Here's a quick summary of what we've learned so far. If you take any complex number z, it has a real part and an imaginary part. The real part is this distance here, x, and the imaginary part is this distance here, y. The magnitude of this complex number, which is over here r, that's the square root of x squared plus y squared, is, of course, got from the Pythagoras theorem. Now, this same complex number can be written as z equals r cosine theta plus I r sine theta. So this x here is r cosine theta, this y is r sine theta, and of course this angle here is theta. The next thing we learned was that if you have two complex numbers, z1 which is r1 into cosine theta 1 plus I theta 1, and z2 which is r2 into cosine theta 2 plus I sine theta 2, if you multiply them together, you get this. Now, if you had three complex numbers, z1, z2, z3, it would not surprise you to know that the answer is r1, r2, r3, and here you would have cosine of theta 1 plus theta 2 plus theta 3. And here you would have I sine of theta 1 plus theta 2 plus theta 3. And now, if you had n of these, z1, z2, z3, up till zn, then you'd multiply their magnitudes together, and here you would have n such angles added together, and of course here too. Now, here's something interesting. Suppose theta 1 and theta 2 are both the same, and let's call that theta. And we can also make r1 and r2 the same. And so if you have z squared, and let's take r1 and r2 equal to 1, this will then be cosine of theta plus I sine theta multiplied by itself, or rather squared, and this then has to equal to cosine of 2 theta plus I sine 2 theta. Now let's see what happens if you multiply this out. You'll get an interesting identity. You'll get cosine squared theta minus sine squared theta plus 2I cosine theta sine theta equal to cosine 2 theta plus I sine 2 theta. Now that's quite remarkable because cosine squared theta minus sine squared theta, that's of course cosine 2 theta. So equating the real parts, we get that cosine 2 theta is this. If we equate the imaginary part, then we get sine 2 theta equals 2 cosine theta sine theta. And so this is a way of deriving this trigonometric identity. But now more generally, so more generally, we have the following. Cosine of theta plus I sine theta taken to the nth power is cosine of n theta plus I sine of n theta. And now this is a very important identity. It tells us that you can relate cosine of n theta to a product of cosine thetas and sine thetas, and similarly for sine of n theta. This is known as De Moivre's formula. I'm now going to derive a very useful and a very important formula for representing this complex number z, which is here r into cosine theta plus I sine theta. And I'll begin by reminding you that cosine of theta can always be expanded as 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial and so forth, and this is an infinite series. Similarly, sine theta can be expanded as theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, etc., etc. We can keep going on. Now, let's add these together. So, z then is r, and I'm going to put in cosine theta exactly the way it is, 1 minus theta squared over 2 factorial and theta to the 4 over 4 factorial. And then I'm going to add on the I sine theta piece. So this will be plus I theta minus I theta cubed over 3 factorial plus I theta to the 5 over 5 factorial. And that's all that I'm going to do. Order theta to the 6th and theta to the 7th, etc. are not included, but we could include them. Now, write this in the following form. I'm going to write this as 1 plus I theta. So I'm just bringing the I theta over here. Plus I theta squared over 2 factorial. And I've done nothing wrong because I squared or iota squared is minus 1, and so that's the minus sign over here. And then the next term I'm going to write is I theta cubed over 3 factorial. And I cubed is I squared, which is minus 1 into I, so that's minus I, and that's the correct sign here. And then we can keep going. And finally, there's I theta to the power 5 over 5 factorial, etc. Now, this is immediately reminding us that this is the expansion of e to the power I theta. And so we have this remarkable formula that any complex number z can be written as the magnitude of the complex number times e to the power I theta. And this is what is known as Euler's formula. Now, there's something very important over here to remember, that if z is written like this or like this and this are equivalent to each other, if I make theta go to theta plus 2 pi, which means that if I go not just by theta but go all the way around, come here and then go by theta, that's theta plus 2 pi, that I will get to the same complex number z. And so if I have e to the I, let's say, pi by 3, or I have e to the pi by 3 plus 2 pi, these are exactly the same. That's because e to the I 2 pi is equal to 1. And e to the I 2 pi times any integer is 1. And that's basically because of the periodicity of cosine of theta and of sine of theta. We all remember from trigonometry that cosine of 2n pi plus theta is the same as cosine of theta. And similarly, sine of 2n pi plus theta is equal to sine theta. And so, e to the I into 2n pi plus theta is exactly the same as e to the I theta. Adding 2n pi does not change the fact that you are at this point in the complex plane. To understand the polar representation of a complex number better, let's work out a couple of simple examples. First, z is 1 plus I square root of 3. We'll first sketch z and then 1 over z. So for z, we go 1 unit this way, that's the real part, and then square root of 3 units this way. And so this is the complex number 1 square root of 3. And if we draw a line that goes all the way up over here like this, then this distance from here to here is square root of 3. This is 1, and obviously this is 2. Now this angle theta over here is cosine of theta equals half, which means theta then is pi by 3. And so we can write the polar representation of this complex number z as 2 times e to the I pi by 3. Now let's work out, so that's z over here. Now let's work out 1 over z. If I use the polar representation, it's so easy because all I need to do is write this as half, and then 1 over e to the I pi by 3 is e to the minus I pi by 3. What that means is that I'll go in the other direction, so theta will be downwards, and I'll only go distance half instead of 2 over here, and this will be the point 1 over z, which is half e to the minus I pi by 3. So the same angle, but in the other direction, that is to say in the clockwise direction. This is anti-clockwise. We can check that we get exactly the same if we look at this z over here and write 1 over z as 1 over 1 plus I square root of 3, and then of course we'd multiply this by 1 minus I square root of 3 and divide by 1 minus I square root of 3. And so this gives 1 minus I square root of 3 divided by 1 plus 3, which is 4. And so this is 1/4 minus I square root of 3 over 4. Now the norm of this complex number is the square root of 1/4 squared, which is 1 over 16 plus 3 over 16, which is the square root of 4 over 16, which is half. And so that's the same as over here. And if you look at the angle, well, that angle will be tangent of theta equals, this is the y, which is minus square root of 3 over 4, divided by 1 over 4. That's tan theta equals y over x, which I'm using. And this is then minus square root of 3. And so then theta from here would be minus pi by 3. And that's exactly what we have over here. But you see that by using the polar form, I could get the 1 over z so much more easily. It's instructive to look at different values of theta, whether you write z as this or as e to the I theta, they're exactly the same. You can see that when theta is 0, then the complex number is here. When theta is pi by 4, then it has rotated around to a position like over here. When theta is pi by 2, then you're on the y-axis, and so z is imaginary. So that's over here. And when you rotate theta through pi, then z becomes -1. Let's look at this problem. We're asked to find all the cube roots of -1. Now, the cube root of -1 can be written as -1 to the 1/3, or you could write it as this. What it means is that if z is the cube root of -1, then when cubed, this should give -1. Since z is a complex number, we can always write it as e to the I theta. And so we have to solve the equation z cubed equals -1 or e to the I 3 theta equals -1. But we can write -1 in an exponential form as well. We could write -1 as e to the I pi, or we could write -1 as e to the I pi plus 2 pi. That is, we could add 2 pi to pi, and that would be e to the I 3 pi. Or -1 we could write as e to the I and add 2 pi to this again. And this could go on, but going further, as we'll see shortly, does not lead to anything new. So we'll just take these three over here. In which case, the first possibility is that e to the I 3 theta is equal to e to the I pi, which means 3 theta is equal to pi. That means theta is pi by 3. Or e to the I 3 theta is e to the I 3 pi, which means theta is pi. Or 3 theta is equal to 5 pi. So theta will be 5 pi by 3. Now, if you were to add another 2 pi over here, that would be e to the I 7 pi, in which case you would have 3 theta equals 7 pi by 3. But 7 pi by 3 is really 2 pi plus pi by 3, and that we've already covered, because when you add 2 pi to theta, you'll get back to the same point. So the 3 cube roots of -1 are z equals e to the I pi by 3, z equals e to the I pi, and z equals e to the I 5 pi by 3. Now, each of these you could write out as cosine of pi by 3 plus I sine pi by 3, and that is, as you recall, half plus I into square root of 3 over 2. If z is e to the I pi, that's cosine of pi plus I sine of pi, and that's just -1. And if you do this, this is cosine of 5 pi by 3 plus I sine of 5 pi by 3, and that is half minus I square root of 3 by 2. And so we have got the 3 cube roots of -1. And as you can check, there are only 3 distinct cube roots, because if we keep adding 2 pi's over here, we will not get anything different. In exactly the same way, we can solve the equation z to the 4 plus 1 equals 0. This is asking us to find the fourth root of minus 1. So z to the 4 is equal to minus 1, or z is minus 1 to the 1/4. How are we to find the fourth root of minus 1? Again, as before, we'll write z as e to the I theta, in which case we have e to the I 4 theta equals minus 1. But minus 1 we can write as either e to the I pi or as e to the I pi plus 2 pi, which is 3 pi. We could add another 2 pi to this, that's 5 pi, or as e to the I 7 pi. And we could keep doing this, but we will not get anything more after these 4 possibilities. If we take the first possibility, then 4 theta is equal to pi, which means that theta is pi by 4. If we take the second possibility, 4 theta is 3 pi, which means that theta is 3/4 of pi. Take the third one, and this gives us theta is 5/4 pi. And finally, 4 theta equals 7 pi, which means theta would be 7/4 pi. If we took over here 9 pi, then 4 theta would be 9 pi, but then theta would be 2 pi plus pi by 4, and that would not give us anything new. So now that we have the thetas, that says that we have the fourth roots. So the fourth root of minus 1, one of them will be cosine of pi by 4 plus I sine of pi by 4, and that's 1 plus I over square root of 2, because cosine of pi by 4 is 1 over square root of 2, and sine pi by 4 is also 1 over square root of 2. And similarly, you can get all the other fourth roots of minus 1. There are 4 and only 4 distinct roots. The rest are exactly the same as we found over here. We have actually encountered our first example of a complex function. And it's a non-trivial example. But let's go back to what a function is. It's a machine. You give it some input, and there's an output. Earlier on, we had taken a real number as the input and gotten a real number as the output. But now, if we give a real number, in this case theta, then out comes cosine of theta plus the imaginary part, which is sine theta. Or equivalently, you could write this as e to the power I theta. So this is an example of a complex function where you give a real number as the input and out comes a complex number. Now, more generally, you could have given over here the complex number z, and out would have come the complex number f of z. So, if you give z equals x plus iy as the input, out would come the real part of f of z, let's call that g of z, and the imaginary part of f of z, let's call that h of z. This would be a real number and this would be a real number. Unfortunately, this is just about as far as we're going to go in discussing complex functions. We've only been able to touch the subject of complex numbers and complex functions. But basically what we did was an extension of what we knew earlier about real numbers and real functions, because we were able to separate every complex number and every complex function into a real part and an imaginary part. Of course, the real and the imaginary parts are governed by the same rules as the rules that we had studied for real numbers. There's lots of surprises
in the theory of complex functions. It's a very beautiful subject, and I hope you will read more about this at some future time.